Now, here's a hard truth. Just because your computer spits out a number, it doesn't exactly mean that that's the right answer. Whether you're solving equations, running simulations, or doing data science, the results you see are always approximations, products of algorithms, not magic. And if you don't know even the basics of numerical analysis, you might not realize when your results are misleading, unstable, or maybe even flat out wrong. In this video, we'll uncover why understanding the fundamentals of numerical analysis is the key to knowing the limitations of computer programs and how that knowledge can save you from costly mistakes. So today, we're going to talk about numerical analysis, and we'll go over one of its fundamental tools called root-finding. So what's numerical analysis? It's all about using computational methods to solve mathematical problems that are too complex for exact formulas. So in finance, this allows us to price complex derivatives, optimize portfolios, and calibrate risk models. In data science, it helps us fit models, look for optimum points, minimize errors, and perform simulations where analytical solutions don't exist. So for example, what's one way to compute for the natural logarithm of 1.10 via numerical analysis? Of course, you simply can just plug this into Excel and the answer is 0.09531. But the point is that even that formula has an underlying methodology using the power of computers and code, right? And that is numerical analysis in practice. Now, doing this kind of simple exercise brings to mind the issues faced when using software and computers to solve real-life machine problems that would have been otherwise invisible to us who use software on a regular basis. Here, for example, one workaround is to use the fact that the derivative of ln of 1 plus x is equal to 1 over 1 plus x. Then getting the reverse operation, integrating on both sides, gives us the integral of 1 over 1 plus x as a numerical solution to ln of 1 plus x. Note that this is a workaround. We have transformed the problem of ln of 1 plus x into another problem to get a computationally tractable solution to the problem. However, they are not the same because the left side cannot do negative numbers, but the right side allows us to do so, so it's not quite the same, although it is a very useful workaround to arrive at a solution. So how do we work this? First, we get the integral of the expansion, which follows a very predictable pattern that can be easily coded via loops to get a solution. And here we plug in 0.10 as x, and we have 0.95093. Had we stopped at the fourth part of the expansion, if we wanted more accuracy, we could have simply added more of the expansion, and we would get closer and closer to the answer of 0.09531. That is what's happening with numerical analysis. So most of the time, our problems are so run-of-the-mill that we can safely work our problems without having to worry about these things. It does not mean that these problems go away. It's just that it's not big enough a problem to worry about. But there might be problems when these issues would pop up unexpectedly. Or the software we are using might require us to encode additional inputs to solve the problem. So it helps to know these kinds of issues. The way, for example, drivers don't have to be mechanics to drive a car, but should know enough of machines to troubleshoot basic stuff or bring it to mechanics before things really break down or go out of hand. That's what we're trying to do. We're still driving the analytical process and the computations and like so, but there'll be times when things can be really complicated and we might have to go to the experts. Now, every time we have number crunching, the computer or our code might store the numbers in a particular way that may create problems for us in a way we do not anticipate. For example, what if a machine or our code only accepts 2 digits to the right of the decimal point? Let's take a look at this example with f of x equal to x squared plus 7x. The input is x equals 0.125, and immediately we have a problem. We might input 0.125, but the machine or our code will only take in 0.12. So immediately there's a round-off error so early in the process. Now, 0.12 squared, that creates errors on top of the original round-off error. This is called propagation error, as the error gets bigger, although there is no problem with the code per se or the algorithm per se. For example, 0.12 squared equals 0.0144 but this gets stored as 0.01 only. In the end, we get 0.01 plus 0.84 is equal to 0.85, but the correct answer is 0.890625. So while the algorithm and code is okay, there are still errors. In real life, we might accept numbers that the software gives us, but we're never sure how correct these numbers are, especially for complicated or even convoluted calculation processes. Which brings us to computer errors. And we already discussed the first two round-off errors, especially truncation, meaning the numbers are just chopped off, or it could be rounded down or rounded up. Or propagation errors, where the round-off errors and any errors that are already there gets propagated through a series of additional calculations. We might once in a while also see this, underflow and overflow. Underflow means attempts to create a smaller exponents are halted, and overflow attempts to create higher exponents are halted. So it can't do very small numbers or very large numbers anymore. And that error message comes out. We move on to root finding. One of the key building blocks in numerical analysis is root finding. That means finding values where the function equals 0. For example, solving for the internal rate of return in investment calculations involves root finding, or looking for the optimum requires finding the zeros of the first derivatives as discussed in our previous videos. So it's a very important procedure for figuring out what the zeros of a function are. And for root finding, we're going to focus on two things, the bisection method and the Newton-Raphson method. Let's use this example, f of x equals x squared minus 10x plus 9 for our examples. And we know that the zeros are at x equals 1 and x equals 9 because this breaks down to x minus 1 times x minus 9. But remember, we're trying to use the computer to find the solution. So we're not going to do factorization like we just did, but we're going to use brute force and ask the computer to compute for these zeros. So how will we do it? We'll focus first on the bisection method. With the bisection method, if a function f of x is continuous and passes through the horizontal axis, then there must have been a point where f of x equals 0. This implies a change in the sign of f of x. So if we went through 0, that means you were going from positive, then 0 to negative, or vice versa. You're going from negative, then 0, then positive. So that's basically the whole idea. So you just keep on splitting the segments into two right in the middle, and hence the name, and find out which segment is there a change in sign, and choose that segment. And then you keep on doing that until you get near enough the zeros. So for example, in this graph, f of a is positive, f of b is negative, then there must be a point between a and b where f of x is 0. So let's get the midpoint of a and b, get the bisection, and we get c equals a plus b divided by 2, and then we look for c. We find c, and it's something like this. Now, choose a segment with a change in sign, and that'll be AC rather than CB. Now, f of A is positive, f of C is negative, then there must be a point between A and C where f of x is 0, the same point that we had a while ago. So we do the bisection for those 2 points. We get D equals A plus C all divided by 2, and then we plot that, f of D. And then again, we have 2 choices for segments, AD or DC. But remember, we have to choose that segment where there's a change in the sign of f of x, and that'll be between D and C. And we repeat the process over and over again until we reach a certain point where the new bisection is near enough 0 that we can already stop. And here, f of E is near enough 0. And we're going to say, okay, it looks like the bisection method already found a 0. This is what it looks like if you start taking a look at numerical examples. And we've provided a spreadsheet for this exercise and all examples in this video. Please visit the video description below to access the Excel file. Here we have to start somewhere called seeding the process, where we set the initial values, and it can be quite arbitrary. This is no trivial matter, because sometimes the wrong initial conditions can set the algorithm off in the wrong direction, creating infinite loops and arbitrary stops. Anyway, here we shall start with 0 and 10. This is our initial boundary conditions, and then try to run our iterations using the spreadsheet that we're providing. So here the first estimate is 5, the midpoint of 10 and 0, And then we continue doing this by the process we laid out a while ago. First estimate is 5, the midpoint of 10 and 0. And we continue doing this by the process we laid out a while ago, leading to 2.5. Continuing with the iteration or loop, the next estimate is 1.25, then 0.625, then 0.9375. And here we see that we appear to be zooming in on one of the zeros, which we know to be x equals 1. So basically, that's what the bisection method does. So the bisection method is a very simple but powerful idea. It's a brute force approach, but its basic simplicity makes it very appealing, especially since computers nowadays are very fast. So you can simply deploy this, write code, and you can come up with this one very quickly. Let's move on to the next procedure, and let's start with the Taylor polynomial and stop at first derivative. Now, given the first degree Taylor polynomial, we equate to 0 and then we solve for x. We have this final equation, which is x equals x sub 0 minus f of x sub 0 all over f prime of x sub 0. And it's called actually the Newton-Raphson method, but we'll just call it the Newton method here. So this is the Newton-Raphson iterative process. It uses a new estimate coming from the old estimate minus an adjustment, negative f of x sub 0 all over f prime of x sub 0. And this is what the formula looks like. Now, let's work on this using our previous function, and this time we get the first derivative as well of f of x. As usual, we see the process with an initial value, and here let's start with the number 3. Note that we cannot start with a value of 5 because that makes f prime 0, making the ratio f over f prime undefined, and the run stops immediately. So going back to the problem, we start with x equals 3. The next estimate is now 0, and because of Excel formatting, it's just showing up as a dash here, but we know that that means 0. So we can copy downwards the cell to replicate running the loop, and now we can see the estimate starting at 3, going to 0, then 0.9, then 0.99, then 1. As we can see, this method converges the solution very quickly. Even if we extend the runs, there are no material improvements in the new estimates anymore, indicating that we have converged to a solution which we know already beforehand to be 1. How about if we started with 2 instead of 3? Here we converge to a solution earlier by 1 iteration. Now, we might be starting with all sorts of initial values near 1, which lead us to the solution of x equals 1. And this might lead us to believe that 1 is the only answer if we didn't know any better. However, we know from our prior knowledge of math that, in fact, there are 2 answers, x equals 1 and x equals 9, but our attempts so far only produce x equals 1. So kindly note that. But if we started with a number closer to 9 than to 1, let's say over here we start with 10, we know the solution does not converge to 1, but it converges to 9. The lesson here is that the solution will generally converge to the nearest 0. If we started here, the solution will roll to A. If we started here, the solution will roll to B. And if we started here, the solution will roll to C. So in the end, we have to ask ourselves, how many solutions are there? In general, we don't really know how many solutions are possible. We might think there's only one answer, and we might stop when we arrive at one solution. In reality, there might be no solution, or one solution, or there could be multiple solutions. In the absence of clever math, we might have to search the whole range of x and look for all possible solutions, which will require fast computers, large memories, and efficient algorithms. This difficulty gets compounded even more when we work with multiple variables and n space. Now, this might require random seeding and so-called hill climbing methods to look for local optima, or more general methods that combine local optimum search with genetic algorithms. This leads us to the question, therefore, all right, so we can start anywhere, but when do we stop? Well, of course, one can say, well, you stop when you hit the answer. Problem with that question is that we don't know the answer in general. That's why we're using these procedures coming up to look for when to stop. Now, this leads us to concept of stopping rules, where we watch the new estimates being generated and compare them with previous estimates. So we could take a look at absolute errors. If the absolute errors, as they change from time to time, from movement to movement, become so small, they already become acceptable to us, then we can stop there. And that's called the absolute error stopping rule. But sometimes, if the numbers are naturally small to begin with, then this might stop the runs too early. So we might want to explore the next one, taking a look at relative errors as a stopping rule. This time we take a look at the percentage change in the movements. And if the percentage change is small enough, we can stop the runs. Or at times you might want to have some mix of the two based on certain conditions that we ourselves set. Finally, it's possible that there are no solutions. So we might want to stop arbitrarily if we hit a particular number of runs or loops, like stop at 25th or 100th iteration and so on and so forth. In this case, stopping does not mean we reach a solution, but rather we hit a roadblock. Otherwise, if we don't put a break to the run, what if there's really no solution? Then the program might just go on an infinite loop that will never stop and will never reach a solution. So it leads to nowhere and we have to stop somewhere. And that's why we need to set the limit to the number of iterations. Now going back to our example, we generated both the delta absolute error. Here, for example, the numbers delta means the changes in the x. And the percentage change will simply just be the delta over the previous number. Now, the idea here is to really monitor the new estimates being generated and knowing when to stop, ideally when the process converges to a solution as shown by the errors, meaning the error is already small enough and we might have to set it, like we might set an error of 0.00001 or something like 0.001%. We have to define that beforehand. So that was the Newton method. It's a very powerful and efficient method for root finding. However, the main problem is that the first derivative has to be computed, and that's not necessarily as easy as in the example. Additionally, if f prime of x is 0, the procedure fails because of the division by 0 problem. So it stops there. Although there are workarounds, the point here is that there are problems with the Newton method, even though it's very, very powerful and it's very, very fast. So now we're ready to go back to the very heart of the issue we raised at the start of the video. Why are the solutions provided by the computer not necessarily the right answer? As we've seen, it's because, number one, machine errors cause distortions to the numerical accuracy. So a weird number comes out unexpectedly, like adding 0.1 and 0.2 and getting 0.3000004, which is very near 0.3, but it's not exactly 0.3. So you get this weird number. Number two, it might be because poor initial value settings or unstable numerical processes cause the procedure to fail. Or maybe there might be no solution at all, as we explained in the iterative processes previously. Or number three, there might be a solution, but it's not unique, and there might be many correct answers when we were just expecting one answer. So we just give one solution where in fact there should be more. And you have to pay attention to that. We're not sure if there's only one answer. Number four, the iteration process might have stopped after reaching its upper bound for number of runs, and it'll give a very poor solution. However, the fact is we need to stop somewhere, and if that stopping rule is hit, then the procedure stops even though we haven't really reached a real answer. So that's the point. When you're working complicated procedures that require numerical solutions, you have to pay attention to the error messages or other cues your favorite computer programs send out to alert you to potential issues. This might be especially true for specialized software to compute for small numbers associated, for example, with time series, ARIMA modeling, for example, or for non-linear optimization like for Markowitz portfolios in finance, or even for machine learning procedures such as cluster analysis that may require minimization or maximization given extensive data, etc. In any case, it is hoped that this video helps you understand the underlying issues related to numerical analysis so that you can temper your expectations that the solution is always available using computer software and quant skills. Because sometimes the computer solution is not really the answer. If you enjoyed this video, please like and subscribe to support the channel, and see you next time!